After 7 months of intense reconstruction of the orbital launch pad and making critical upgrades to both the first and second stage vehicles, SpaceX has finally conducted its second integrated flight test of Starship. And wow, was it worth the wait. From the moment the Super Heavy booster jumped off the pad, this launch was a night and day difference from the first attempt. Most notably, SpaceX was able to keep all 33 of Booster 9's Raptor 2 engines running at peak performance for the full duration of the boost phase of flight. This allowed them to successfully reach stage separation and pull off something that I don't think many of us expected that they would accomplish on their first try. Of course, I'm talking about a near-perfect hot staging of Ship 25. Although both vehicles would end up being lost, with B9 exploding during its boost back burn and S25 being destroyed for currently unknown reasons, this was undoubtedly a fantastic success that SpaceX will continue to build upon. Even though they made this drastic improvement look easy, there was a lot of work that went into preventing a repeat of what occurred during the first integrated flight test. In this two-part episode, we're going to examine all the major upgrades that SpaceX made as a result of the data collected from IFT-1, starting with a tale of two boosters, Booster 7 and Booster 9. If you're looking for a super in-depth analysis of the engineering challenges that had to be overcome, then make sure you subscribe to the channel, because you've come to the right place. My name is Zach Golden, and welcome to another CSI Starbase Deep Dive Investigation. Hey everyone, thanks for joining us. After the first integrated flight test of Starship, there were a lot of major changes that needed to be made in order to improve the odds of SpaceX successfully making it to orbit on their second launch attempt. For the first few months after IFT-1, most of our attention was rightly aimed towards reconstructing the foundation and upgrading the blast surface under the orbital launch mount. We covered that pretty in depth in a two-part episode a few months ago, so if you haven't seen those, I recommend checking them out after this. This system ended up performing flawlessly, and after the launch, Elon shared a photo of the surface of the booster Bidet system, allowing us to see that it did in fact survive in perfect condition. As a result, SpaceX has officially pulled off something that decades of research from NASA launch pad design engineers said was impossible. This system was designed in a way that should allow for continuous usage without the need for refurbishment. Even as they continue to increase the thrust output from future versions of the Raptor engine, they will easily be able to adjust the pressure and volumetric flow rate of water in order to compensate. To celebrate the success of the booster Bidet system, we are offering these super comfortable Stage 0 t-shirts at a 10% discount for the first 100 customers. In the spirit of the season, we have also released a hoodie version of this as well. You can find the link to the CSI Starbase store in the description below. We want to thank you for supporting our channel. So, with the addition of this active flame deflector system, we should no longer have to worry about the destruction of Stage 0, and now we can focus on the improvements made to the first and second stage vehicles. During IFT-1, SpaceX was able to accumulate a ton of data related to the performance of the booster. But due to the fact that they were unsuccessful in reaching stage separation, they didn't exactly have the opportunity to test the performance of any of the systems on the ship. No second stage ignition, no partial orbit around the Earth, no controlled re-entry, and no splashdown off the coast of Hawaii. Because of this, I think we can all agree that in a lot of ways, Booster 7 was the weak link in the chain. The simple fact is, if the booster doesn't do its job during liftoff and the entire ascent phase, then nothing else really matters. With that said, there were some extremely critical changes that would need to be made in order to make Super Heavy more reliable. Some of these upgrades were things that you could consider to be a natural progression in the development process. Alterations that were already in progress long before the first launch attempt. But others were changes that SpaceX realized needed to be made after reviewing the data collected during IFT-1. And this presented a bit of a challenge. As an expected consequence of the insanely fast manufacturing process at Starbase, a lot of these alterations would have to be retroactively made after the next booster was already at the end of the assembly line. Booster 9 was fully stacked on October 27th of 2022, and by the time of IFT-1, which occurred 6 months later, it had already completed its initial cryogenic proof testing and was in the process of having its 33 Raptor engines installed in the Megabay. So, as you will see, the Super Heavy team really had their work cut out for them. Some of these things we will discuss may be changes you already know of, but our goal is to go into as much detail as possible, and even the most hardcore Starship fans should learn something that they didn't know before. Hopefully by the end of this, you will leave with a greater appreciation for the incredible amount of work that went into preparing for this second trial. To accompany this episode, TheRingWatchers have released an amazing, easy-to-follow article that goes into detail about literally every noticeable change on both the Starship and booster. It actually covers more than what we will be mentioning here today. So if you want even more information, make sure to check out the article that I've linked in the description, and also make sure to follow TheRingWatchers on X for even more updates related to Starship manufacturing. Alright, so as we get into this, the first upgrade we need to discuss is the latest version of the Raptor 2 engines. As a quick review, Booster 7 was the first booster to use the Raptor 2 engines, which was a considerable improvement over the Raptor version 1.5. Not only was it significantly lighter, weighing about 20% less than its predecessor, but it also improved the thrust output from the engines from about 185 tons up to 230 tons. One of the major upgrades that SpaceX made to the Raptor 2 engines was not able to be incorporated on Booster 7, and unfortunately this turned out to be somewhat of an issue during the first integrated flight test. Of course, I'm referring to the new electric thrust vector control system, which made its debut appearance on Booster 9. The transition to electric TVC comes with several important benefits. The first of those benefits is weight reduction of the vehicle. This is a result of eliminating each of the massive hydraulic power units, the stainless steel aero covers used to protect them, and all of the associated pipework and hydraulic fluid running to each of the center 13 gimbling engines and the common manifold used to supply them. Next is reliability. In my opinion, a big downside of these HPUs was their tendency to break. It seems like a lot of maintenance was needed in order to keep them operational. At one point, SpaceX had to remove one of Booster 7's HPUs and replace it with one that was mounted on Booster 8, which they had decided not to fly. After the first scrubbed launch attempt of B7 and S-24, we watched as SpaceX spent a full day tending to these HPUs, along with some frozen valves on the booster QD. Another problem with these HPUs is that if you lose one during flight, then it immediately doubles the workload on the remaining unit. Based on our observations, we believe that Booster 7 was capable of losing one HPU and still operating its TVC system for all 13 of the center gimbling engines. This means that there was most likely a single common manifold supplying hydraulic fluid to each of these engines. The main problem with this is that if something were to happen to cause a major leak in the hydraulic fluid manifold, like, say, an engine explosion damaging the pipes, then once the fluid runs out, the booster would instantly lose its ability to steer itself. And as most of you all know, Booster 7 did in fact end up losing all control of its thrust vector control system about 85 seconds into flight. As a result, the ship and booster began cartwheeling through the atmosphere until the FTS system was able to destroy the vehicle. Now, we can't say for certain whether or not the HPUs simply stopped functioning, or if there was a major hydraulic leak which eventually led to the inability to supply fluid to the TVC actuators. But based on my observations, I'm assuming that it was the latter. Early in flight, we saw a pretty massive fireball with black smoke shoot out of the back of the booster, which in my opinion, could have been a result of hydraulic fluid leaking into the exhaust plume. Later in the flight, we also noticed a fire raging inside of the engine skirt, which also could have been a result of either an engine explosion or hydraulic fluid burning inside of the skirt. Both of these are possibilities, but neither of them can be confirmed. Either way, by switching to electric TVC, the possibility of a hydraulic fire occurring in the future has been completely eliminated. Fire prevention is extremely important, and it's a topic that we will revisit several times throughout this episode. Beyond this, a major advantage of the electric TVC system is that SpaceX should no longer have to worry about a complete loss of steering capability because all 13 of the center gimbling engines should now be operating independently of each other. So if one malfunctions for some reason, it should have no effect on the other 12, and they should easily be able to pick up the slack. At that point, the only thing that could cause a total failure would be an issue with the batteries used to power the electric actuators. But I would have to assume that SpaceX has redundant batteries running in parallel to prevent this from occurring. Alright, so now that we have covered the changes to the Raptor 2 thrust vector control system, it's time to address the other major concern related to these engines. As I mentioned before, one of the biggest issues that SpaceX is worried about is engine explosions and fires within the aft section of the booster. Let's start with the explosion risks. The need to protect the vehicle from sustaining serious damage due to rapid, unscheduled disassembly of one or multiple Raptor engines has always been a high-level priority for SpaceX. This has been one of the most common factors that Elon has mentioned over the past few years when discussing booster reliability. As you might be able to guess, the best way to protect against these localized overpressure events and the shrapnel that accompanies them is to enclose each of the 33 Raptor engines in blast-proof containment boxes. Whether it's intended to function as blast-proof shielding or simply as an engine shroud, these enclosures can be found on nearly every rocket engine out there. In the past, Elon has mentioned that on future versions of the booster, they plan to eventually do away with this shielding entirely, and essentially have 33 naked engines hanging down below the vehicle. This would reduce the weight of the vehicle by an estimated 10 tons, which is a lot. But in my opinion, this is a pretty lofty goal. Until the Raptor engines reach a level of reliability equivalent to that of the Merlin engines used on the Falcon 9, we should not expect to see that happen. To put that into perspective, as of the time of writing this, there have been 273 Falcon 9 launches and 8 Falcon Heavy launches. That's 2,673 times the first stage Merlin engines have flown, and in that time, there has only been a single in-flight failure of one of these engines. Achieving this level of reliability could take quite some time, because SpaceX is continually pushing the boundaries of physics to increase the performance of these engines. As of right now, there's really no end in sight when it comes to locking in the design of Raptor and settling on a final production version. So until that happens, SpaceX will most likely continue to incorporate this engine shielding on both the booster and Starship. Booster 7 was only the second booster to ever be outfitted with engine shielding, but it was the first to perform engine testing with that shielding installed. Because of this, I think it's safe to say that initially, SpaceX engineers weren't really sure exactly how much shielding would be necessary in order to contain explosions from these Raptor engines. With that said, I think their original goal was to accomplish this using the least amount of material possible in order to keep the weight of the vehicle down below their target of around 160 tons. Fortunately, on July 11th of 2022, they learned that the initial design that they had settled on would not be enough. I think this was a good thing, because it allowed them to get a huge head start on a redesign, which would later turn out to be super necessary. Those of you who have been following this program over the past few years will remember the explosion that occurred during their first ever 33-engine spin prime test on Booster 7. And for those of you who are new fans of Starship and don't know what I'm talking about, this clip from NASA spaceflight is easily the most overused footage in my episodes, but I think I can finally retire it after this one. Before we get into the details about the damage that occurred, let's quickly identify the individual components that make up the shielding of these engines. This will become important when it comes to appreciating the significance of the upgrades made to Booster 9 and understanding why they were necessary. Thanks to these amazing renders and animations from Chameleon Circuit, we should be able to visualize all of these details pretty clearly. Let's start with the center engines, and then we can work our way out. Before any of the shielding is installed, there is a large circular frame with 13 smaller circles inside of it, one for each of the center engines. This frame is roughly 13 inches or 33 centimeters thick and is secured to the bottom of the thrust puck. Once the frame is mounted, circular collars are bolted around the rim of each of the 13 engine positions. These have a small lip which hangs over the inside edge of the rim. We will explain what this is used for shortly. The next step is to lift the engines into position and attach them to the thrust puck. These engines come with the lower part of the shielding pre-installed, which reduces the amount of work that has to be done later. This section covers most of the main combustion chamber assembly. After the engine is fully installed, two halves of an upper ball joint section are joined together inside of the circular cavities of the frame. These cover all of the engine plumbing and wiring harnesses, as well as the linear actuators that control the position of the engines. These ball joints have a low clearance with the circular collars to prevent flames from penetrating through the gap. While the engines are gimbaling, it maintains the seal as the engines swing up to 15 degrees in any direction. Next up is the floor panels. These are flat panels which cover all of the exposed framework. This protects all of the remaining pipework and electrical components mounted in the cavity between the bottom of the thrust puck and the engine power heads. I wouldn't consider this to be part of the blast shielding, however. I think its primary purpose is for thermal protection. This will be particularly necessary during the landing burn when the booster is rapidly descending into its own exhaust plume. There is a layer of black flame-resistant material attached to the bottom for this purpose. Finally, a cylindrical steel barrel that encloses the power head of the engines is installed as well. Each of these half sections are reinforced on the inside with ribs that add extra strength to the walls of the enclosure. There are several pieces of this assembly, like the one shown here, which were left out because we didn't think they were necessary for this explanation. Also, the order of operations for installation may be slightly different in real life, but the goal here is to identify most of the critical components of the shielding. Alright, let's move on to the outer 20 Raptor boost engines. Just like the center engines, it's necessary to create fully enclosed containment boxes for these as well. The shielding used in these locations is a bit different, however, because there's no need to account for any gimbal motion since these are locked in position. While it would be ideal to use the same type of shielding found on the center engines, it's not really possible due to the presence of the Raptor QD ports and the rim used to lock the booster onto the hold-down arms. This shielding also had to be shaped in a way that would allow for the hold-down arms to retract into the launch mount while the booster is lifting off the pad without colliding into the shielding. So the first step in assembling these protective enclosures is to install all of the divider walls that separate each of the 20 engines. As you can see, these dividing walls come attached to a flat panel which flares outwards at the bottom. The reason for this tapered look is to create space for the hold-down arms on the OLM. Once all of the divider wall sections are bolted into place, the next step is to install all 20 of the boost engines. Just like the center engines, the bottom plate for the shielding comes pre-installed on these Raptors before they are lifted into position. This lower plate is bolted to the bottom of the divider walls and has a lip that wraps around the bottom of the outer skirt plate. These are also bolted on in order to allow them to be quickly removed during engine swaps. After all the additional pipework needed to connect to the overhead gas and liquid manifold is installed, they can begin attaching the rear walls of the enclosure. Ideally, these walls should protect the center engines from shrapnel in the event of an explosion from one of the boost engines. This works as long as the wall isn't ejected outwards by the resulting overpressure. On the flip side, they also protect the boost engines in case the shielding from the center engines is blown off. Finally, the curved panels that cover the power head from the outside are installed as well. This completes the boost engine shielding assembly as it existed on Booster 7. It's important to note that as an added bonus, these enclosures should do a good job of containing fires and preventing them from spreading to adjacent compartments. But their main purpose is to prevent collateral damage from shrapnel generated during an engine explosion. I don't think the containment box is actually intended to remain fully intact after an engine run, however, because as far as I can tell, there's nowhere for the rapidly expanding gases to escape during the resulting overpressure. So when that happens, something has to give. With that said, I think it's reasonable to assume that these are designed for the outer covers to be blown off first. Alright, so now that we have an understanding of all the different components that make up the protective isolation shielding, let's return to the July 11th, 2022 anomaly. We aren't going to focus on why this occurred, because I covered this in depth in a past episode, which you can find up here if you want more info. Instead, we're going to take a look at the aftermath and discuss the important lessons that SpaceX engineers were able to learn as a result. So, as Booster 7 was lifted off of the launch mount a few days after the explosion, it was immediately evident that this massive external overpressure event caused some pretty serious damage to the engine shielding. Most notably was the fact that it completely blew out 8 of the 20 curved protection panels that covered the power heads of the outer 20 boost engines. After the booster rolled by LabPadre's Rover 2 camera on its way back to the build site, we got our best look at the damage, but it was difficult to see inside to determine what else may have been affected. But thanks to these images from Starship Gazer, we can see some of the damaged material that was left over before it was eventually scrapped. Even though they are pretty smashed up, it's clear that most of these panels appear to be rectangular in shape. Looking at the square corners, we can safely assume that these are panels that came from the inner wall of shielding for the boost engines. On some of them, we can even see the brackets that were originally on the divider walls, which appear to have been ripped free. But what about the center engines? Well, in another shot from RGV Aerial, we can see that some of the cylindrical sections for the center engines were damaged as well. This piece appears to have been removed manually, so we don't know if it was actually blown off in the explosion. What we can say for sure is that the flame-resistant coating on the outside of the panels were completely roasted. But I would say for the most part, they seem to have done their job. It's extremely obvious, however, that the boost engine blast shielding was in serious need of an upgrade. So when Booster 7 returned to the launch site, the center engines had been removed, and this is when we realized that some of the divider walls had actually been damaged as well. In this shot from Starship Gazer, you can see at least 2 had been fully removed, and another was missing the outer plate. It would end up taking several months for the compromised shielding to be replaced. At the time, we didn't expect it to be that difficult, because the equivalent shielding for Booster 8 was likely already in production or possibly even ready to go. But as we later found out, the real reason it took so long is because SpaceX was now aware that this shielding was insufficient and needed to be completely redesigned. Waiting for version 2 of this shielding for B7 would have taken months, and pushed back the launch date even further than it was already slipping. So SpaceX engineers did the best they could to improve on what they already had available. On January 8th of 2023, B7 returned to the launch complex for the 7th time after finally completing its robustness upgrades, which were first mentioned by this tweet from Elon 7 months before its maiden launch attempt. B7 now had its shielding reinstalled, and everything looked mostly the same as it did originally. The only difference that we were able to detect were new weld lines in the locations where they had previously used bolts to attach the divider walls to the flat outer panel of the skirt. It seems that SpaceX decided that these bolts were not strong enough to hold these panels together, which is a possible sign that the original divider walls did in fact sustain some damage during the July 11th explosion. We also noticed a few horizontal welds, which were an indication of additional supports welded to the inside, which would help prevent the walls from bending in either direction during an internal overpressure event. Given that the original bolt holes for attaching the divider walls were nowhere to be found, I believe the identical shielding that was intended for Booster 8 may have been retrofitted with these changes and then installed on Booster 7. So, now B7 was ready for flight, even though SpaceX was well aware that it wouldn't perform well in the event of an engine rud during its inaugural flight test. On September 21st of 2022, Elon tweeted the following statement: "Our focus is on reliability upgrades for flight on Booster 7 and completing Booster 9, which has many design changes, especially for full engine rud isolation." In a follow-up tweet, he said, "That's the plan. We're taking a little risk with flying Booster 7, as engine isolation was done as a retrofit, so not as good as on Booster 9. As it turned out, during IFT-1, we saw several exterior panels blown off at the skirt of the vehicle at 2 different instances. The first was clearly visible in the SpaceX launch footage, where we can see an explosion occurring 28 seconds into flight. This is the moment where SpaceX says they lost communication with Engine 19. We can only assume that the power head of Engine 19 exploded at this moment. It's tough to see in this footage, but Elon confirmed that after this event, the engine shielding on engines 17, 18, 19, and 20 were all blown off. I think that in order for this to happen, the divider walls between the left and right adjacent engines must have been completely destroyed during the overpressure event caused by the exploding power head. Somehow, this managed to reach all the way to engine 20, which is pretty impressive. At first, the 3 adjacent engines continued running. However, at T+33 seconds, engine number 18 also suffered an explosive shutdown. We can't say for certain, but it's highly probable that this is a direct result of damage sustained during the explosion of engine 19. It's important to note that the shielding for the HPU on that side of the vehicle also appeared to have been blown off during this event. We can confirm this thanks to the fire that was briefly visible in the area where the protective aero cover should have been located. We don't know if this was related to the other 2 engine explosions, or if it's just a coincidence that it occurred around the same time. As I mentioned, there was another explosion that took place shortly after. This one was a bit different than the first, so we will discuss it in a few minutes when it becomes more relevant. Anyway, now that we know that the modified engine shielding was insufficient for isolating ruds and preventing damage to adjacent engines, let's take a look at how SpaceX addressed this issue with Booster 9. The damage sustained during both the July 11th anomaly and the first integrated flight test made it pretty clear that the containment boxes for the outer 20 engines were not really doing their job at all. The spin prime explosion resulted in complete destruction of the rear walls of the enclosures, and the engine 19 rud during the launch was able to take out multiple divider walls, resulting in catastrophic damage to adjacent engines. On the plus side, it appears that the center engine shielding seemed to hold up well and not cause any issues. With that said, as Booster 9 was in the process of having its engines installed following the integrated flight test, we were on the lookout for hints of how the engine isolation boxes were going to be upgraded. Thanks to the 9-month head start they had as a result of the July 11th event, most of the parts were already on site by that time. On February 20th of this year, Chief from Randolph Visuals posted this image on X, which showed brand new divider wall panels for Booster 9 being offloaded at the production site. These divider panels featured pretty significant upgrades to the structure. Unlike the thin, single-walled panels on Booster 7 shielding, these new dividers featured double-walled panels, which are a lot more heavy-duty than the original design. As we mentioned earlier, SpaceX switched from bolting the walls onto the flat outer panels in favor of welding them on. They had also added 2 horizontal braces, which are intended to prevent the wall from being ripped free or bending to either side. On these new divider walls, SpaceX engineers dramatically increased the number of horizontal braces, adding 7 additional braces for a total of 9. These are also clearly visible from the outside view of the engine skirt thanks to the weld marks. Additionally, you can also see that the 2 panels that make up the wall are bent outwards on the inside edge. The previous design had a flat mounting bracket where the rear wall panels of the containment boxes would bolt to. These new mounting surfaces allowed for curved panels to attach to the divider wall, forming a more cylindrical enclosure. The curvature of these walls eliminates most of the hard corners from the original design, which might become areas of high stress concentrations. As a result, you can see that the total volume of the enclosure has been slightly reduced. It seems that just like the divider walls, SpaceX decided that 2 layers of protection was necessary here as well. Behind the curved blast shield, there is an additional flat panel similar to what was originally present on the design for Booster 7. We believe that this creates a secondary containment shield so that in the event of an explosion, the curved walls will not be ejected outwards towards the center engines, and will instead impact this wall. This actually works both ways by preventing the shielding from the center engines from damaging the enclosure for the outer 20 boost engines. I think this double containment also makes it significantly less likely for shrapnel to penetrate through both layers. The same can be said for the divider walls. This secondary wall may also act as a thermal shield, which will be very helpful during the landing burn while the booster is falling into its own exhaust plume. Looking at this again from the outside, there's one additional detail most people noticed the first time B9 rolled out, which is this black strip around the bottom of the engine skirt. Contrary to what you may have heard elsewhere, we don't really think there is anything special about this. This strip is just an extension of the black thermal protection panel that already existed on the bottom of the lower plate for Booster 7. In my opinion, it's not really meant to provide any structural reinforcement. As far as we can tell, the cylindrical outer panels that cover the power head are basically the same as they were on Booster 7, although they may be slightly thicker. Unfortunately, we don't really have a way of verifying this for sure though. The fact that there is little to no change to these panels may suggest that they're intended to be the weak point of the enclosure assembly. Essentially, if there's an overpressure from inside of the containment box, this is designed to be the part that breaks free. These covers are the only part of the enclosure that can be ejected outwards without damaging something else on the vehicle, so this makes sense. When all is said and done, this upgrade should result in a significant improvement in performance in the event of an engine rut. We've now covered how to protect against explosions that originate from inside of the Raptors, but there's also fires that can occur on the outside of the engines. This is where a fire suppression system becomes necessary. When it comes to fire suppression, ideally the best place to start is by doing everything you can to prevent the fire from happening in the first place. This is the idea behind the Firex and detonation suppression system on the orbital launch mount, which we've mentioned in previous investigations. As for the booster, there was a lot of effort that went into addressing this issue as SpaceX was developing the upgraded Raptor 2 engine. In particular, there was a high priority placed on reducing the likelihood of fuel leaks developing within the plumbing of the engines. Methane leaks are never a good thing, especially when they happen within the general vicinity of a massive open flame. As you can imagine, these leaks have a tendency to cause fires, which is something that we witnessed in some of the early high-altitude flight tests. By removing many of the bolt-on flanges of the engine pipework and replacing them with permanent welds, a lot of these leaks were able to be prevented. Now, they didn't disappear entirely, so there's still some work left to do in that department. But less leaks means a reduced probability of fires developing around the power head of the Raptor engines, especially while they're inside of that enclosure. As mentioned in this tweet by Allan posted on July 14th of 2022 in response to the Everyday Astronaut, this is part of the reason why they eventually want to get rid of the engine shielding. But because this is currently not feasible, they have to do something to protect against the possibility of creating a MOX bomb inside of the engine shroud. A MOX bomb is basically the combination of gaseous methane and oxygen. The higher the concentration of these gases inside of a confined space, the more explosive the outcome. To prevent this from occurring, SpaceX planned to purge the entire engine shroud continuously during flight. On each of the outer 20 engines, there was a flexible hose coming from the top of the power head that runs down to the bottom of the engine bay and ends in a double-sided T-shaped vent. These are also present on the 13 center engines. You can see the orange flex hoses moving around in this footage from SpaceX. This is Booster 9, but it should have been the same for Booster 7. In order to supply gas to these vents and purge the inside of the enclosures, SpaceX needed somewhere to store the gas on board the vehicle. On every booster from B7 onwards, there are two sets of large aero covers going up either side of the liquid oxygen tanks. On the windward side, there is a large set of strakes which are used to cover the COPVs needed for startup and relight of the center 13 engines. Until recently, we believed that there was likely nitrogen stored within some of the COPV tanks, which would be used to suppress fires by filling the enclosures with inert gas. It wasn't until SpaceX began upgrading this system on Booster 9 and 10 when we were actually able to figure this out. This is where the post-launch retrofits come into play. At the time of the first integrated flight test, Boosters 7, 8, 9, and 10 all had a smaller set of chines on the leeward side of the vehicle. These are similar to the strakes, but their aerodynamic properties are different, so they are referred to as chines. I'm not really going to go any deeper into that because it's irrelevant. For the longest time, we never really knew what was under these chines because we never saw them uncovered. At least until Starship Gazer took these pictures of Booster 10 while it was in the rocket garden receiving the upgrades we are about to discuss in a few minutes. Gazer was lucky enough to catch this at the perfect time with the strakes removed to allow us to see what was hidden underneath. So, thanks to these images, we realized that there were two sets of long, small diameter tanks under each of the strakes. Zooming in closely, we can see a label on one of them which identifies it as a CO2 tank. At the bottom of these CO2 tanks, there were pipes that enter the vehicle near the bottom of the aft section, just above the engine skirt. These relatively small CO2 tanks are what was used to purge out the engine bay of Booster 7. For confirmation, I was able to locate video evidence of this system in action, which previously went unnoticed until we had a reason to look for it. This footage is from Booster 7's 33-engine static fire test, which took place at 3:14 p.m. on February 9th of this year. Nearly 2 hours after the static fire, as B7 was nearing the end of the detanking procedure, I noticed this event occur. I believe that what we are seeing here is the CO2 being purged out of the bottom of the engine skirt. We can verify where this is coming from thanks to the presence of cold water vapor coming off of the pipes that run from the bottom of the CO2 tanks into the aft section of the booster in this location. This venting continued for nearly 2.5 minutes, which is about the time it should have taken for Booster 7 and Ship 24 to reach main engine cutoff and stage separation before second stage ignition, had they made it that far. One thing that is pretty apparent here is that there is a relatively low volume of CO2 gas visible coming out of the aft section of the vehicle. Because of this, I would say that the goal here was to reduce the explosive potential of a methane-oxygen mixture within the enclosed space by diluting the oxygen gas with CO2. In other words, a mixture that would, under normal conditions, result in a detonation may still ignite and burn, but it wouldn't actually explode. This is a form of pressure mitigation, which is important because overpressure within the compartment would likely blow out the protective panels and cause extensive damage to the engines. Some of you may be wondering why CO2 is being used in this system instead of nitrogen like the detonation suppression system. Well, both nitrogen and CO2 can be used for fire prevention, but from my understanding, CO2 is better for smothering active fires. After asking around a bit, it seems that CO2 may be better for electrical and chemical fires and is less harsh on sensitive equipment like all of the electronics and wiring harnesses used in the engine bays. With that said, we know that this system was likely running for the entire ascent phase, as Allan said it would be. But how did it perform? Well, unfortunately, during IFT-1, we saw many fires that were raging inside of the booster's engine skirt throughout its ascent. This was shown best in the footage taken by Cosmic Perspective and the Everyday Astronaut. When we look closely, we can see that these flames were mostly visible between the engines. Since there is nothing hanging below the protective shielding other than the 33 engine bells, I think it's safe to assume that these fires were emanating from within the engine enclosures and somehow were escaping out of the bottom floor or the rear walls of the enclosure. As I said before, it's possible that these fires were a result of hydraulic fluid that was leaking within the aft section of the vehicle. But it's equally possible that these fires were related to fuel leaks coming from the booster and Raptor engines. It's tough to say for sure, but what we do know is that roughly 64 seconds into flight, the second engine bay explosion that we mentioned earlier took place. When we slow down the footage, you can see that the shielding from at least 2 or 3 of the engines is ejected off of the side of the vehicle. But this time around, there were no signs of engine shutdown to accompany the explosions, and all 3 in this location somehow continued running for the remainder of the flight. With that said, I think that what we were seeing here was an accumulation of methane and oxygen gas within the engine skirt that managed to find a source of flame, causing it to detonate. So we have 2 different types of explosions that occurred, and this is one that I think SpaceX was somewhat surprised by. But the data that they gathered during this flight was enough to tell engineers that the fire suppression system in Superheavy's aft section was extremely insufficient. In the list of 63 corrective actions from the FAA that was posted to X by Allan, Item C33 under the Booster Reliability Improvement section mentioned the need to better manage engine bay pressure by increasing fire suppression capacity by 15x. This is where the more challenging post-IFT-1 retrofits to the booster come into play. 2.5 months after IFT-1, long after Booster 9 had its engines installed, this massive cylindrical tank was spotted as it was being rolled over to the megabay. A few days later, Mauricio from RGV Aerial caught this image of B9 with the large tank installed in the location where the smaller 2 CO2 tanks were previously mounted on B7 through B10. After these were installed, SpaceX upgraded the size of the chines so that they were nearly identical to the strakes on the windward side of the booster. This kind of gives a good idea of how much larger these tanks are. The tops of these aero covers also became the perfect place to mount the Starlink antennas, which were previously located on the HPU covers for B7. Meanwhile, 2 weeks later at the launch site, as construction on the water-cooled flame deflector system was nearing completion, a new vertical tank was installed near the high-pressure nitrogen gas storage tanks used to force the water out of the deluge system. This vertical tank is used for storing liquid CO2, which is converted into gaseous form inside of this vaporizer before it's sent to the launch mount. It travels underground between the large water pipes until it reaches this leg where you can see an insulated pipe leading up to the inside of the launch deck. From there, we can only assume that it's routed to the booster QD, where it's injected into the large tanks on the booster. This vertical storage tank was a replacement for a smaller CO2 tank which was originally installed in front of the integration tower back in June of 2022. This tank was no longer large enough to supply the upgraded CO2 tanks on the booster, so once the new system was in place, it was removed. When Booster 9 finally rolled out for the first time with engines installed, we noticed that another big change related to the system had been made as well. Some of you may have likely seen the new vents that were installed on the aft section of the booster between the stringers. There are 18 of these vents in total. We believe there will be 20 if not for the presence of the two stabilization sockets on either side of the booster which seem to get in the way for some reason. These valves are located just below the point where the aft dome is welded to the ring wall, which means they are several meters above the actual engine bay. There is a huge amount of pipework crammed into this space, which is known as the aft end cavity. Most notably are the large pipes supplying liquid oxygen and methane to the engines. There are also smaller manifolds circling the entire aft section, which send hot vaporized oxygen and methane back to their respective fuel tanks for the autogenous pressurization system. A leak in any of these connections can result in an explosive mixture forming in the area above the engines. When we look at the shielding design from B7 from the inside, we can see that there was a plate on top of each of the enclosures. We didn't mention these before, but these prevent fires from the inside of the engine boxes from reaching the sensitive equipment above. Keep in mind, there are a lot of wiring harnesses and smaller pipes up here, which aren't shown in the model. You can really get an idea of how busy it is up here thanks to this image from Starship Gazer. Because of this top plate, we believe SpaceX thought it might only be necessary to purge the actual containment boxes for each of the engines. With the newer design, we can see that there is still a top cover plate for the engine enclosures, which continues to protect against fires spreading into this area. But it seems like whatever SpaceX learned during the integrated flight test told them that it was also necessary to purge the space above the engines. Keep in mind that we really don't know if this was already being done on Booster 7. But in the aft end cavity environment failure section of the 63 corrective actions, item C2 also lists increasing fire suppression capacity by 15x. This suggests that it may have existed previously, but like the engine bay purge system, it was not potent enough. It's interesting that this was actually mentioned as a failure of the aft end cavity. This is something I really wish we had a bit more information on because we weren't able to find any evidence of it in the footage. Either way, as soon as the flight test had concluded, these vents were added onto Booster 9 as a retrofit. They were later added onto Booster 10 and still have to be added on Booster 11 and 12. We believe that from here on, they will be added much earlier in the fabrication process inside of the Star Factory, instead of after the boosters are fully stacked in the Mega Bay. Anyway, when Booster 9 rolled out for the first time with engines installed and all of these upgrades complete, we also noticed a ton of wiring taped around the engine shroud. There was one for each of the 20 engines. These wires entered the skirt through a small hole at the bottom. Referring back to the list of 63 corrective actions, items C18 and C19 under the Raptor leak mitigation section mention adding one methane sensor per engine bay and a ground test campaign to better characterize typical engine leakage. I believe that's what we're seeing here. Methane sensors inside of the engine compartments with temporary wiring on the exterior of the vehicle for ground testing purposes. So with these new sensors installed, SpaceX was able to perform a 33-engine spin prime test on August 4th. Nearly 4 hours after the spin prime was conducted, we saw the first test of the new engine purge system. As you can tell, this is far more CO2 gas than the original design. I'd say a 15x increase means that they are no longer trying to simply dilute oxygen concentrations present in the explosive mixture. Instead, the goal is to completely flood the engines and aft cavity section with CO2 in order to ensure that there will be no chance of combustion occurring in those areas. After the first 33-engine static fire test, B9 was sent back to the Mega Bay, and when it returned, most of the wires for the alleged methane sensors were no longer visible. I think it's possible that they were moved inside of the aft section, but there's a chance that they were completely removed. Honestly, I'm not sure how much use they will actually be during flight operations. Just like B7, we should probably expect this system to be active from the moment of engine ignition and all the way through stage separation. It may also be needed for the center 13 engines that are active during boost back and the landing burn as well. But since the suppression system should be running through the full duration of the boost phase, it's not like the sensors will be needed to tell the system when to activate. In my opinion, the only real value they get from monitoring methane gas leaks during flight at this point is to tell them that they need to further increase the capacity of the system if it happens to fail again. Anyways, we saw the test repeated after the second 33-engine static fire test and the full stack wet dress rehearsal. For some reason, they tend to do this after detank is complete. This is how I was able to find the Booster 7 fire suppression test because I realized that the best time to look for it was near the end of detanking. It's great to see these changes being implemented in real time, and I think this was a major contributor to the success of IFT2. but more on that in a few minutes. The one remaining issue related to the Raptor engines is one that I wasn't really able to gather much information on. During IFT-1, before the vehicle even left the ground, we saw that 3 of the Raptor engines failed during engine startup. This is easily the biggest area where everyone was hoping to see some improvement as engine testing began on Booster 9. But during both of the 33 engine static fires, we saw the same thing occur again. On the first 33 engine test, there were 4 engines that shut down after ignition. The second attempt was slightly better, with 3 of the engines suffering from various issues, resulting in early shutdown. Good news is that Booster 9 would have been able to lift off successfully with 3 engines out. But after what happened the first time, I'm sure that most of us were hoping to see at least one successful attempt at lighting all 33 engines with no issues before the next launch attempt, but that didn't happen. It was hard not to be extremely worried that the same thing would happen again during the second integrated flight test. The main reason for this is because, unlike the other topics that we've covered, it's nearly impossible for us to see what changes were being made in this area. But as you all know by now, SpaceX really knocked it out of the park with this one. When Booster 9 lifted off the pad, it had all 33 engines running, and they remained that way for the entire boost phase. What was really awesome is that this time around, the engine telemetry diagram popped up 10 seconds prior to liftoff instead of after the vehicle had already cleared the tower. This allowed us to see the engine startup sequence that SpaceX went with for this booster. We believe this startup sequence is something that SpaceX has been continually tweaking over time as they try to determine what works best. When we slow down the footage, we can see that the 13 center engines are ignited in 2 separate groups. This pattern seems extremely random, as we were expecting them to be lit in opposite pairs in order to keep the thrust balanced. Surprisingly, this is just about as unbalanced as it can possibly get. But after stepping through this frame by frame, there's only about 1/6 of a second difference in between the startup of the first and second groups. Because of how fast this occurs, I can only assume that balancing thrust is not really a concern for the center engine startup. So after the first 2 groups are ignited, there is a full 1 second gap before the next group of engines are started. This time, 15 of the outer 20 were lit. You can see that there was a lot more symmetry in this third group of engines, with them being ignited in groups of 3, skipping 1 engine between each group. It seems like one of them actually turned on a bit late. We don't know if this was intentional or if there was some sort of delayed ignition. Exactly 1 second later, the last 5 engines in Group 4 are successfully ignited, and then it takes just over 2 seconds for the booster to perform engine checks while holding its throttle. Once this is complete, it takes 2.5 seconds for it to throttle up and finally begin accelerating off of the hold-down clamps. From here on, Booster 9's performance was absolutely flawless through the boost phase. Not a single one of the engines shut down during this time. While this was phenomenal, I was personally a bit disappointed because I was hoping that at least one of the boost engines would explode so we could see how the shielding would perform this time around. Because that didn't happen, there was really no data gathered in this area, which means that we should not expect any further changes to the boost engine shielding as of right now. As for the fire suppression system, we did not see any onboard fires nor gas explosions during the entire flight. This is also great news because it means that the 15x upgrade seems to have worked. As expected, this system was active during the entire boost phase of flight. You can see the CO2 gas curling over the bottom of the engine skirt when you look at any of the amazing photographs taken from the launch. This close-up from SpaceX shows the CO2 being sucked back into the exhaust plume immediately as it passes over the edge of the skirt. If you look closely, you can also see it coming down from between the engines as well. The best views of the fire suppression system came during the most engine cutoff as the outer 20 engines began to shut down in groups of 5. Oddly enough, this shutdown sequence is exactly what I was expecting this startup sequence to look like. What you will notice here is that as the engines shut down, the CO2 is no longer being sucked into the plume, causing it to begin expanding outwards away from the vehicle. It's extremely rare that I ever get a chance to do this, but I have to correct Scott Manley here because what we are seeing here is not cold propellants continuing to flow out of the engines. I think that would be a sign of a major failure of the main fuel and oxidizer valves on every one of those Raptor engines if that was the case. Anyway, the fire suppression system continued running for several seconds after MECO, but appears to shut down after the initiation of the flip maneuver. This is an interesting sign because it means that the booster may have the ability to turn this off for the outer 20 boost engines, while keeping it running for the ones in the center. But it's tough to tell whether or not this system is still active after this point. Next up, we have the boost backburn, which is where things finally begin to go south for Booster 9 after an otherwise perfect hot staging event. After dropping down to 3 engines and separating from Ship 25, Booster 9 began reigniting the 10 center engines that shut down after the hot staging event. All but one of them were able to successfully restart. This was a really weird coincidence because it's exactly what Ryan Hansen Space depicted in his orbital flight test animation 7 months ago. We aren't going to go into why this happened for now. Instead, we're going to focus on the topics related to lessons learned from IFT-1. So during the actual flip maneuver, Booster 9 lost 3 of its engines. After the flip was complete, it seemed to coast for a few seconds before it quickly lost all of its remaining engines. Because the top of the booster was now facing back towards the ground, we weren't able to observe the engines as they were shutting down. But even from this angle, we could see that at least 3 of these suffered catastrophic explosions. The third and final engine rud was significantly more violent than the first 2. Shortly after, we can see 2 shiny objects ejected from the back of the booster. It's tough to say for sure, but I'm assuming that what we are seeing here are 2 halves of cylindrical shielding that surround the power head of the center engines. It appears that 2/3 of the exploding engines were able to be contained by the shielding, but one of them was unsuccessful. With that said, knowing that one of them failed, it will be interesting to see if SpaceX will find it necessary to further reinforce the center engine shielding, or if they will view this as an acceptable performance. Moving on, the final major issue that had to be addressed following the first integrated flight test was the flight termination system. As most of you know by now, after the flight termination command was given to both the ship and booster, it took roughly 40 seconds for it to destroy the vehicle after the charges had detonated. Elon originally predicted that recertifying this system would end up being one of the longer lead time items when it came to getting ready for the next launch, but this ended up not being the case. On May 15th, the new FTS system was tested on the Booster 6 test article at the Massey's test site. This test seemed to go pretty well, and after it was completed, the FTS boxes on both the ship and booster were upgraded. We were initially expecting some sort of large detonation cord to be used, as mentioned during Elon's Twitter Space discussion following IFT1, but that ended up not occurring either. Instead, the charges which were previously located on top of the weld line for the booster and ship common dome were moved a few meters higher so that they would now be at the bottom of the methane tank section. The old FTS boxes remained, but were no longer used. It seems that SpaceX decided that it wasn't really necessary to punch holes in both tanks. By rapidly depressurizing the methane tank alone, it should either quickly cause an engine shutdown, or may even completely destroy them in the process. Depressurization of the methane tank would result in a large pressure differential between the fuel tanks, which would likely cause the common dome to implode, similar to what we saw happen on Ship 27. We will discuss that more in part 2 of this episode. To further help with unzipping the methane tanks quickly, it appears that the size of the charges used in the FTS system was increased as well. On November 9th, a Starship Gazer captured this moment when the FTS charges were taken from their safety storage container and escorted over to the ship and booster. SpaceX wasted no time getting these installed, and once they were finished, Jack Beyer captured this image, allowing us to see what the explosives looked like once they were mounted. Comparing this with images of the FTS charges on Booster 7 and Ship 24, we can see that these are nearly double the size. While we were hoping that these would never need to be used again, during the second integrated flight test, we were able to see how much more effective this improved FTS system was. After the stage separation and flip maneuver, the 12 center engines that relit were shutting down one by one. Immediately after the final engine flamed out, the automated flight termination system decided that the show was over and triggered both sets of charges on the booster. This time around, there was no slow depressurization of the fuel tanks. Booster 9 immediately exploded into thousands of pieces. I should note that there has been no official statement from SpaceX confirming that the FTS was triggered on the booster. There's a lot of speculation that this explosion was due to a collapsed downcomer inside of the liquid oxygen tank. This could very well have been the case, although I find it very interesting that there appears to be a flash coming from the exact location where the booster's FTS charges are located. Shout out to Ryan Hansen Space for angle matching this with his model. This is something that we will need to wait for additional information on, but in the meantime, we are more confident about the fate of the second stage vehicle. Ship 25 continued on its flight path after successful stage separation, reaching a max velocity of 24,124 km per hour and an altitude of 148 km before all 6 of its engines shut down shortly before the end of its planned 6-minute burn. Ship 25 was incredibly close to reaching the next major milestone of entering the coast phase and gliding the rest of its way to the re-entry point over the Pacific Ocean. Just like Booster 9, the AFTS was triggered and the vehicle was destroyed. Unlike the booster though, we don't really have any idea of how long it took for the FTS to break the ship apart, but it was successful all the same. The only surviving piece of the ship was its nose cone, which was captured in this shot by Astronomy Live. This nose cone proceeded to burn up on re-entry, which was captured by onlookers in Puerto Rico. Now, I know that all of you are probably wondering why I didn't go into any detail about hot staging. Well, I think that even though the hot staging ring is technically a part of the booster, it makes more sense to discuss it when we talk about the changes to Ship 25. On top of that, this episode was already long enough as it is, so in part 2, that will be the first thing that we cover. And trust me, there's going to be a lot to discuss there. In that episode, we will also take some time to evaluate the possible changes that will need to be made in order to ensure that SpaceX is finally able to achieve all of the goals set for the current phase of flight testing. If you enjoyed this deep dive investigation, then do us a favor and give this video a thumbs up. And if you haven't done so already, be sure to subscribe to the channel so you don't miss part 2 and all of our future episodes. As you can tell, we put a lot of effort into these investigations, so we appreciate your support. On that note, if you would like to help us continue to produce content like this, then please consider becoming a monthly supporter on Patreon or joining as a member of the channel on YouTube. You can find the links to those options in the description below. I want to say a huge thank you to Chameleon Circuit, who spent countless hours creating all of the detailed renders and animations used in today's episode. By becoming a member, you are also giving us the ability to compensate them and all of the other 3D artists we work with for the incredible amount of work that goes into these productions. Of course, none of this would be possible without the footage from RGB Aerial, Starship Gazer, Kevin Randolph, Ryan Hansen Space, Cosmic Perspective, and the Everyday Astronaut, as well as the 24-hour live streams from LabPadre and NASA Spaceflight, and everyone else whose content was used in today's episode. So thank you for all the incredible work you do documenting the Starship development process. All right, everyone, hope to see you all in part 2. For now, this is Stage Zero Zach, signing off.